let's start lecture 39, and the course is corrosion protection methods. So we'll continue our discussion on inhibitor and associated corrosion protection. Now we have understood that how to calculate corrosion inhibition efficiency, and then also we have seen that where we can use inhibitors, as well as we have also understood that these inhibitors are to be added at a very small dose, and also it gives us the benefit of excellent corrosion protection. Now we'll try to look at classification of inhibitors, and within those classifications we'll try to understand the mechanism how those inhibitors work. Now to start with, let us look at the classification of inhibitor. So when you talk about that, so there could be broadly three segments, or let's say one is inorganic. Within that inorganic we can have two broad, which is anodic, another one is cathodic inhibitor. And within the cathodic we can have some sub segments, like one is poison, like arsenic, bismuth or tin, and there could be something called precipitator. Broadly they are mainly basically phosphates. Okay. Now when we talk about organic, and in case of inorganic, inorganic anodic, we can think of some of the examples like chromate, nitrate, phosphate, or there could be molybdate, etc. Now there could be another variations, which is organic. Now in those organic, mostly they are film forming. And one of the sub variations of organic inhibitor is vapor phase inhibitor. Then we have another one is some of the inhibitors, they try to change the environmental conditions. So mainly they either reduce the hydrogen ion concentration or remove some of the corrosive agents like oxygen. So those are called inhibitors changing environment condition. So there could be two variations. One is scavenger, another one is neutralizer. As the name suggests, scavenger means it scavenges out some of the corrosive agents like oxygen, or neutralizer is which neutralizes hydrogen ion and then reduces the acidity of the solution. So these are broadly some of the classifications. Now the mechanism how it works, let us look into that part. Now most of the times they are actually those inhibitors like organic inhibitors, they try to get adsorbed on the surface. Even inorganic inhibitors, they get adsorbed on the surface, and then they either block the cathodic sites where cathodic reaction happens, or block anodic sites where anodic reaction happens. So, if you block either of these two, then definitely the total rate of corrosion would reduce, because for the complete corrosion process, both anodic and cathodic reactions are to continue simultaneously. So, one of them is stopped, then other one is also uh, stopped to a great extent, or also stopped. Okay, so or break. You break one of those processes, then you break the entire cycle. Now, in some cases, they actually try to passivate the surface. Okay, so we know passivation actually improves the corrosion rate to a great extent. Some of the substances, like mostly anodic inhibitors like chromates, they actually take the potential into the uh, passive zone for an active passive metal or alloy. So, we will see that. Now, if we try to look at the mechanism point of view, so let us look at anodic and cathodic. How inhibitors work. So, if we talk about anodic, it influences anodic process, either blocking anodic sites or passivating the surface. Fine. Now, what it does, if we try to look at from the mixed potential point of view, so if you see this E versus log I plot, so let us say this is the situation here. So, this is my E core and this is I core. This is anodic process or anodic polarization. This is cathodic polarization. So, now what can happen? The plot, this anodic part can move like this. So, actually the anodic reaction or the anodic polarization is getting influenced. And now you could see clearly that the E core, the new E core, so this is E core, let me put it in terms of INH. So, INH means inhibited, and this was, we can put it as, this one we can put it as blank. Okay. Now, if you see the corrosion potential that moves up, so that means anodic polarization point of view, if you notice that the E core moves to the positive direction in compared to E core in blank condition after the addition of inhibitor. But if you see the I core, that I core also has dropped. So, this will be my I core and this is inhibited I core. So, this corrosion current density also drops. Now, two effects, one is anodic potential goes up, Second, corrosion current density drops. So, if we try to look at the cathodic inhibitor, it actually influences cathodic process. Fine. Or it actually blocks the cathodic site, or at times deposit leading to break in cathodic reaction. We will look at that part. So, this belongs to let us say poison, which is arsenic. Okay. It actually deposits on the steel surface, and it actually does not allow the hydrogen evolution reaction, which is the cathodic reaction. Now, if we look at the mixed potential again, these are cathodic and anodic process. Okay. This is E core blank, and this is I core blank. Okay. Now, here it actually influences the cathodic polarization. So, this line moves like this. So, this line, that anodic cathodic polarization line, moves like this. So, now you could see the potential. This is E core inhibited, and this is I core inhibited. You could see that the corrosion rate reduces, at the same time E core drops. So, here two effects again. This is cathodic potential drops, corrosion rate drops. So, that is the basic difference. Now, there are some inhibitors which actually influences both anodic and cathodic part. So, those are called mixed inhibitor. So, there if we try to look at again mixed potential, so now cathodic line shifts like this, anodic line shifts like this. So, now you have this is E core inhibited, which is mixed inhibitor. Now, this potential, depending on the dose of anodic and the influence of that mixed inhibitor on the cathodic or anodic reactions or polarization, this potential can move up compared to this potential or can move down, that relative influence on the anodic and cathodic reactions. But actually you are saying this is my I core blank. Blank means where you do not have any inhibitor, and this is my I core inhibited. So, we could see that the corrosion rate reduces from this value to that value. So, this is also giving inhibition effect on the metal corrosion. Okay. So, now if we try to look at both the situations, if we try to look at from the potential point of view. So, if we see the potential point of view, let us say this is cathodic part, cathode, so which is positive, and anode which is negative. Now, initially let us say this is my potential distribution. Now, once we have anodic inhibitor, so this will be so this potential goes up as we have seen. Now, if it is this is anodic, now if we talk about the cathodic one, in case of cathodic one, this potential drops down. So, this is cathodic. Now, in this case we are talking about this potential and this potential, that difference is shrinks. Now, when it shrinks, actually what happens? So, it leads to driving potential what we have between that cathode and anode, that reduces. And once it reduces, if we have a particular resistance value of that electrolyte, then I would also reduce, or current density would also reduce. So, that means it is a direct influence on the corrosion rate of the metal. So, that is what the basic mechanism how the anodic and cathodic inhibitor or mixed inhibitor work. Now, if we look at some of the examples of anodic inhibitor, cathodic inhibitor or mixed inhibitor. So, examples, so for example, chromate. Now, how it works, we can also get an idea. Now, if we consider active passive metal, let us say this is my active passive metal, the anodic part. Now, iron is dissolving. Now, if we consider chromate, then it can have this reaction. Okay. Now, this reaction can have its own polarization, and this is highly cathodic in nature. So, now that polarization can intersect, that polarization line for this reaction can intersect the polarization, anodic polarization part in the passive zone. So, this is the cathodic polarization. And this is my IP, which is equal to I chord if we go to that passive range, and the passive range is, this is the passive range. Actually, this inhibitor, once we add, it takes the potential of the anodic part towards positive direction and fixes it at passive range, and we get a very low corrosion rate. So, this is kind of passivator, we can say passivator. Okay. So, similarly, we can have nitrate. Then we can have phosphate. So, those are some of the examples. Even molybdate. Okay. So, for example, sodium molybdate forms a complex passivation film on iron surface and it protects it. In fact, this molybdate is very costly and it can also passivate uh, in the presence, it can actually passivate in the presence of oxygen. Okay. So, oxygenated condition, this molybdate can give you very good protection. Now, let us look at some of the examples of cathodic inhibitor. Mainly polyphosphate kind of inhibitors we use. So, this what it does, it actually bonds with divalent calcium and other ions to form positively charged colloidal particles which are attracted to the cathode and forms a protective film. So, it actually forms a protective film on cathode. So, these actually forms positively charged colloidal particle with a divalent metal ions like calcium plus plus. So, they will form, these particular colloidal particles are attracted towards negatively charged cathode. Fine. So, that gives the film and protects it. Zinc is a very good cathodic inhibitor, zinc salts. It also provides it specifically cathodic inhibitor in cooling water system. So, they generally this zinc salts, they act synergistically. So, what is synergistic situation here? So, zinc salts are blended with chromate sometimes. So, we get both the effects like inhibitor, one inhibitor acts like cathodic, another inhibitor acts like anodic. So, we have a synergistic influence on the corrosion rate of the metal. So, that reduces the corrosion rate to a great extent. Now, we can also have poison like arsenic. So, how it works? So, if we have hydrogen evolution reaction is the cathodic reaction and it can be broken into few steps. So, like that we can break into steps. So, what arsenic oxide, if we add it, so mainly in the form of arsenic oxide, so that can react with adsorbed and then it can precipitate arsenic plus H2O. Fine. So, you can say that this is 3H2O. So, this is 6, this is the balanced one. This arsenic what is deposited on the metal surface, that does not allow this particular hydrogen which is evolving to get absorbed on the surface. So, hence a hydrogen evolution reaction, this particular reaction slows down. So, if it slows down, definitely the requirement of electron reduces and you get a low corrosion rate. Now, there could be the examples of mix inhibitor. So, the mix inhibitor works in 3 different ways. One is physical adsorption, then chemissorption, we can also have film formation. Okay. So, for example, if we talk about physical adsorption, we can have positively charged surface and negatively charged inhibitors can get attracted to the positively charged or vice versa. So, if it is negatively charged, then positively charged inhibitors can get attracted, and that will prevent the cathodic or anodic processes. Now, in chemissorption, so this is basically examples of physical adsorption. So, those inhibitors get adsorbed on the surface. In case of chemissorption, so it's a almost similar kind of situation, but what happens, let us say it's a positively charged. So, some of the ions like chloride ion, they can act as a linkage of the inhibitor which is positively charged. So, this is the inhibitor, fine. So, now this chlorine ion acting like linkage or the ligament, and they would get a strong bonding. So, that is a kind of chemissorption activity, and it also gives you very good corrosion protection. Now, film formation, it same like what we have seen in case of anodic protection, anodic inhibitors. So, the properties of the film, so film formation is nothing but those inhibitors are actually forming some sort of passive film on the metal. Like example, chromate, molybdate. So, those are the kind of inhibitors we can think of. Now, we can also talk about organic inhibitors. So, they generally find application in application wise, if we consider in oil industry. So, oil and gas corrosion can be reduced to a great extent. So, they are not like cathodic or anodic inhibitors, but they can influence the cathodic processes or anodic processes depending on its character. So, it is basically the cathodic area as well as anodic areas they can get attracted to, and then they can block those reactions. Now, example is monoamine or diamine, those are the examples. So, what they how do they form? They actually again adsorption works here, and cathodic type of inhibitor. So, cathodic type of inhibitor means positively charged inhibitor. They get attracted to negatively charged metal surface. So, this is a kind of cathodic nature, or it can also like anodic inhibitors or negatively charged inhibitors or anodic inhibitors. A kind of anodic nature. It is not about anodic inhibitor or cathodic inhibitor what we have discussed. They have that nature that it can have positively charged or negatively charged uh, terminals, and those terminals get attracted to positively charged now metal surface. That way it works. Now, in organic inhibitor, one particular example is vapor phase. So, when we talk about vapor phase inhibitors, this is interesting. So, these are like one example is cyclohexylamine carbonate. So, this is one such example, vapor phase inhibitor. Now, these are actually high vapor pressure substance. So, they can easily, if you keep it in a closed chamber. So, the condition is it has to be closed chamber, and there it is not kept close to the metal surface. So, this is kept little away from the metal surface. What they can do, they actually sublimate easily because of the low vapor pressure, and then on the metal surface they can deposit back, and when it deposits back it forms a few monolayers on the metal surface, and then it actually prevents contact with water. So, when it prevents contact with water, definitely corrosion rate would reduce, because water is one of the carriers for charges, and if we actually reduce the moisture, corrosion rate reduces greatly. So, this is working like sublimation and then subsequently condensation, and prevents water connect. Fine, that reduces corrosion rate, and that actually reduces corrosion rate. Now, if we talk about some other inhibitors like scavengers, so which are actually coming under the segment of changing inhibitors, changing the environmental conditions. One is scavengers, example like ammonia sulfide or N2H4, which is hydrazine. So, they are very good scavengers for oxygen. Now, if you have dissolved oxygen, this can react with oxygen and then it can form ammonium sulfate. Or if we talk about hydrogen, it can actually form nitrogen plus 2H2O. And in fact, this nitrogen is gaseous, so it also acts as a scavenger because it removes oxygen. Sometimes in the laboratory scale, in order to do deaeration, we do it using nitrogen. We send nitrogen gas at the bottom of the holder where electrolyte will be kept. So, if we just slowly bubble out nitrogen, that actually scavenges out oxygen, dissolve oxygen. So, this also acts as scavenger, but at the same time this hydrogen can react with oxygen and dissolve oxygen and also removes oxygen by combining it with hydrogen and then forming H2O. So, this one for example is we are talking about safety as well as toxicity. So, this is considered to be carcinogenic. So, nowadays there are regulations not to use this hydrogen. So, now people have started using some modified scavengers like carbohydrazide or hydroquinone. So, these are modified to avoid the carcinogenic effect of hydrogen. So, this is about scavengers. Then we can also talk about neutralizer. Example is typical example is morpholine or cyclohexylamine. Those are some of the neutralizing inhibitor. What they do, for example, if we have CO2 or SO2 or H2S or organic acid, so those cases it actually leads to increase in hydrogen ion concentration. How? For example, CO2 can react with water, it can form H2CO3, which is carbonic acid, and it can break into H plus plus HCO3 minus. So, you could see that hydrogen ion is concentration is increasing. SO2 also can react with H2 and form H2SO3. So, this is also increasing. This is also acid, also an acid, increases the hydrogen ion concentration. So, these neutralizer actually takes care of that hydrogen ion and then reduces the acidity of the solution. And if you reduce the acidity of the solution, corrosion rate would definitely reduce. So, these are some of the examples of different inhibitors and how it works. Finally, let us look at how to calculate the dose of inhibitor. Now, the basic formula looks like this. So, if you want to find out W in terms of kg of inhibitor, so let us say one such inhibitor is sodium chromate. So that would be written as the volume of the water which is to be inhibited into the concentration in ppm. Now, volume of water, if I write in terms of liter, now we know that 1 liter of water is equivalent to 1 kg of solution or water. Now, we can convert this into volume. Instead of volume, that volume in terms of kg we can write because it is in terms of liter, and concentration ppm is basically 1 part per million. So, we can write 10 to the power minus 6. So, then this equation can boil down to this: V kg into x ppm divided by 10 to the power 6. So, for example, if anyone wants to calculate, let us say calculate dosage of in let us say 4 lakh liter water, and we know that and that concentration to be maintained is, let us say 10 ppm. Now, this 10 ppm I think must have been achieved after looking at the laboratory test, that it gives fairly around 90% or 95% efficiency. Okay. So, this is a kind of a prior test, so that we need to have 10 ppm of the inhibitor. So, then we can calculate in terms of kg by looking at this formula. So, 400 liters mean 4 lakh liter means 400 kg of water into 10 ppm divided by 10 to the power 6. This is the amount of inhibitor that will be needed. So, we can calculate. So, 4 kg. So, like that way we can also calculate the dosage of inhibitor, but before that we need to find out this: what could be the optimum dose that should be used by looking at different aspects of the equipment or the material which actually is exposed to a certain medium or electrolyte, and it is also having some functions. So, the inhibitor must not influence those functions, specific functions, adversely to a great extent. So, it would affect, but that should not be too much. So, then only we can make use of this inhibitor, and at the same time, if you see that 10 ppm is a very, very small dose, and that is what the inhibitor works. So, let us end here on the inhibitor part. We will talk about the coatings in next few lectures. So, till then, thank you.